The human eye that enables us to view is a very complex organ. Let us first study its structure. The white protective membrane that is seen when looked at the eye directly is called the sclera. It is a tough, opaque, fibrous outer layer of the eyeball. The circular colored part is called the iris. The color of the eye is determined by the color of the iris. The central transparent area of the iris is called the pupil. The iris works like the shutter of a camera. It absorbs most of the light that falls on it and allows a part of it to pass through the pupil. The amount of light that enters the inner parts of the eye depends on the size of the pupil, which is controlled by the muscles present in the iris. In bright light, the iris contracts the pupil to restrict the light, whereas in dim light, it widens the pupil to admit more light into the eye. The eyeball that contains different parts of the eye is roughly spherical in shape with a diameter of 2.5 centimeter. A transparent protective membrane called the cornea covers the small bulged portion at the front of the eyeball. In fact, the iris and the pupil lie behind the cornea, the crystalline lens, and the retina are some of the other important parts of the eye behind the cornea. The crystalline lens is held in its position by the ciliary muscles. The retina is a film of nerve fibers covering the curved back surface of the eye. It detects the presence of light and its color and sends this information to the brain through the optic nerve for further processing. The retina is able to detect the light and its color because of the presence of sensors called rods and cones. The rods are sensitive to low light, whereas the cones, which require a greater intensity of light, are sensitive to color. The portion between the cornea and the lens is filled with a watery fluid called the aqueous humor. The space between the lens and the retina is filled with a jelly-like fluid called the vitreous humor. Now let us study the working of the human eye. Light entering the eye is first refracted by the cornea. The refractive power of the cornea is large and fixed. The refracted light is then incident on the iris. The crystalline lens is just behind the iris, and light after passing through the pupil falls on it and is again refracted to form a sharp image on the retina. For an object to be seen clearly, the image must be formed exactly on the retina. The crystalline lens along with the cornea is able to refract the light that enters the eye to form a sharp image on the retina. The eye is able to focus objects at different distances sharply on the retina by changing the focal length of the crystalline lens. The process of adjusting to different object distances by changing the focal length of the crystalline lens is known as accommodation. Ciliary muscles help in adjusting the focal length of the crystalline lens. Ciliary muscles are in relaxed state when an object at infinity is sharply focused on the retina. In this case, the focal length of the crystalline lens is the maximum and is equal to the diameter of the eye. When the object is close to the eye, the tension in the ciliary muscles increases and the lens becomes more bulged with reduced radii of curvature. The reduction in the radii of curvature of the crystalline lens reduces its focal length also. But the focal length of the crystalline lens cannot be reduced beyond a limit. Hence, there is a limit for the closest distance for which the lens can focus light on the retina. This is called the least distance of distinct vision, or near point, represented by the letter D. Usually the value of D is taken as 25 cm for a normal eye. The greatest distance for which the lens of a relaxed eye can focus light on the retina is called the far point. The far point of a normal eye is at infinity. We can summarize the three important functions of the eye as follows: admitting appropriate amount of light, refracting the light to form a sharp image, collecting and sending information about the image to the brain for further processing. Now let us discuss some common optical defects in the human eye. The most common defect of the human eye that is found in aged persons is presbyopia. The ability to focus on near objects diminishes with age. This is known as presbyopia. The near point changes with age. For a 10-year-old boy with good health, the near point may be about 7 to 8 cm. This changes with age and may even reach 2 meters for an old person of the age of 60 years. Hence, aged people cannot see objects placed at normal distances of about 25 cm. The incoming light rays are refracted to focus behind the retina. Presbyopia can be corrected by using an appropriate converging lens. Another vision defect that is similar to presbyopia is hypermetropia, or farsightedness. Note that presbyopia is caused by old age, whereas hypermetropia is a vision defect that can be observed in persons of any age. A person suffering from hypermetropia will have normal vision when looking at objects at the far point. But the objects that are close to the eye are focused behind the retina, and as a result, vision is blurred. The defect caused by hypermetropia can be rectified by using a convex lens of appropriate focal length. When a converging lens of suitable focal length is used to rectify either presbyopia or hypermetropia, the image of the object is formed at the near point of the person. For example, let us find the power of the corrective lens used by a person suffering from hypermetropia with near point at 2 meters. Given that the near point of the person is 2 meters, but for a normal person the near point is 0.25 meters. In case of the person suffering from hypermetropia, an object placed at 0.25 meters is focused behind the retina. If a corrective lens is used, it must form the image at a distance of 2 meters. This image will act as an object for the eye lens. That means if U is equal to 0.25 meters, then V must be equal to 2 meters. Substituting these values in the lens formula and solving for the optical power, we get power P is equal to 3.5 diopter. Another commonly observed eye defect is myopia or nearsightedness. An optical defect in which distant objects appear blurred because their images are focused in front of the retina is called myopia or nearsightedness. The person suffering from myopia will have perfect vision when looking at objects close to the eye. But in the case of an object at a faraway place, the eye produces more than required convergence, and as a result, the image is formed before the retina. The effects of myopia can be reduced by using a concave lens of suitable focal length. A defect of vision caused when the cornea is not spherical in shape is called astigmatism. Because of the non-spherical cornea, the eye lens will have different curvatures in different planes. Light in one plane is focused properly on the retina, and objects in that plane are visible clearly. Light from a perpendicular plane is focused at a different location other than the retina, resulting in blurred view of the objects lying in that plane. Hence, a person suffering from astigmatism cannot see all directions equally well. Astigmatism can be corrected by using a cylindrical lens of desired radius of curvature with an appropriately directed axis. We know that light rays, when incident on a lens, converge in the case of a convex lens and diverge in the case of a concave lens. The degree of convergence or divergence depends on the focal length of the lens. If the focal length of a lens is small, then the convergence or the divergence of light is more. On the other hand, if the focal length of the lens is high, then the convergence or the divergence is less. The physical quantity, that is a measure of the convergence or divergence of light introduced by a lens, is called its optical power. The optical power of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at a unit distance from the optical center. You know that a light ray, when incident parallel to the principal axis, after refraction by a convex lens, passes through its principal focus. If the ray is incident at a height h from the pole, and the deviation of the light ray or the angle through which the light ray converges is d, then tan d is equal to h by f. If h is equal to 1 unit, tan d is equal to 1 by f. But as per definition, tan d for h equal to 1 unit is the power of the lens. Therefore, optical power P is equal to 1 by f. That means optical power of a lens is the reciprocal of its focal length. The SI unit of optical power of a lens is dioptra and is indicated by D. Power of lens is 1 dioptra if its focal length is 1 meter. Power of a lens can be positive or negative. As per the Cartesian sign conventions, focal length of a convex lens is positive and that of a concave lens is negative. Hence, the power of a lens is positive for a converging lens and negative for a diverging lens. Note that the focal length and hence the optical power of a lens depends on the medium in which the lens is placed. For example, a converging lens in air with focal length equal to 20 cm is made of glass of refractive index 3 by 2.